It's usually like 7 minutes long. Yeah, that's true. It's just the same chorus over. Yeah. Really? Yeah, I really like long charger. It's like 5.5 minutes. The more technical, like. You don't have to. The more time. Yeah, I'll do it tonight. Those are like the classics. Like, that's what made the Beatles so popular.
Might be sensible.
There's high energy music, and high energy music was like just coming out in like late 60s. Yeah, I mean, it really depends on the band though, because I mean, if it's a very technical band and they want to demonstrate their skill on the instruments.
We had to do like some work to get connected to the and it started driving. And then as I was like to reassemble it, I found another program.
Yeah, but I'm taking a break.
Right, so I have a couple of homeworks left here. I'll pass these around. If anyone didn't get it last time, just try to pick it up. I'll be stuck with them. Here, I'll just raise your hand if you need it, and we'll get it to you. All right. Couple housekeeping things. Next Monday we're going to have our quiz number 2. That's going to cover everything on chapter 2. We're done with that now. And so we'll make the homework due on that day as well. I think I already announced that. And I got a couple questions about homework. Just want to reiterate, I hope everybody's clear with the homework thing, right? You don't need the book to do the homework. There's a document on the website that has all the homework problems and all the homework solutions. So just use that, and that way everything will definitely line up with what you need. Okay, any other questions? General stuff? No. So last time, what did we talk about? I mean, really, last time it seems like we mostly did examples. So hopefully those examples coupled with the the homeworks and all that type of stuff should put you in good shape for next week's quiz. We haven't gotten any homework questions yet this semester. Please bring one in if you have one, because that's, I think, one of the best ways to get an idea of where students, where the gaps in understanding might be. As far as the quiz goes, it's not going to be like the first one, the online one. This will be pretty similar to one of your homework problems in terms of difficulty and all that type of stuff. So you're not going to have some huge 50-node circuit. You're also not going to have some very simple one with just 2 nodes. It's going to be, most of your homework problems are somewhere 5, 6 components, 5, 6 branches, etc. So last time, okay, we're done with that. So chapter 3 then. So chapter 3 is on mesh and nodal analysis, and this is going to be us solving really a lot of the same problems that we were in the previous chapter. The big difference being that now we're going to have a more systematic way of approaching these things, and it's not going to be, I guess what I'm trying to say is the steps won't be different every time. It'll be pretty uniform set of things that we're going to do. Now that being said, the math is a little bit more difficult, I don't think in absolute terms, but it's just you're dealing with matrices and systems of equations, and there's a very specific way that you have to set things up. So once you get the equation set up in the matrix form, it's actually pretty easy to solve. You plug in your calculator, et cetera, and you're done. But getting those equations in the right form can be a little bit tricky. If you don't know how to do matrix math on your calculator, please, read something about that online or whatever. I'm sure most of you have done it in the past at some point, but refresh yourself on that. So, chapter 3. Mesh and nodal analysis. Okay, so nodal analysis is the one that we're going to tackle first. These two techniques are actually the same technique, okay? Because what you'll see is later on, we can do analyses that are hybrids of both, nodal and mesh. The best way to describe these, the more generic way of describing these, is just defining systems of equations to solve circuits. So, right, you know that, let's say we have a circuit with 5 nodes. Okay, we want to know the voltages at those 5 nodes. You need 5 equations in order to solve. So nodal analysis will have us using KCL. Mesh analysis will have us using KVL. You can use combos between them. You find your 5 equations, you set them up into your matrix form, and then because these are linear equations, you can just invert the matrix and solve. Now we're going to go through all that in a slower manner. But that's really the basic gist of it. Okay, so nodal analysis is based on analysis of nodes, as the name suggests. And we're going to use KCL. We're going to build a system of linear equations. And the reason why it'll be linear, the equations will be linear, is because of the circuit components that we have. We're not going to really deal with nonlinear systems in this course, at least not too much, if at all. But the reason why it's linear is because the system is composed only of voltage sources, current sources, and passive elements like resistors and so on. So how can we solve this once we have our system of equations? Like any system of equations, what we're going to do is we're going to substitute, and then we're going to use matrix math. So the basic form of equations that you're going to see, it's going to look a lot like this. So you'll have like like this. So you'll have, let's say for example, two currents, okay, that are known. So we know that I equals V over R, or you could also say 1 over R to the negative 1 times V, right? So we have a matrix here that's going to be an n minus 1 by n minus 1 matrix. And then we have V1 and V2. Okay, so this matrix right here represents the admittance. We call it the admittance matrix. Okay, it can be represented by Y. These are the current injections into the nodes, and we'll talk about what those mean in a second. Okay, so we know this, we can invert this equation, this matrix, and move it to the other side and solve for this. Okay, that's the basic gist of nodal analysis. We know these two. Okay. Sorry, I'm just trying to see if I want to reorder one thing here. Okay, so I want to do one example before we jump into this part, so let me look in the book again. Okay, so what we'll do is we'll do an example that uses figure 3.4 from the text. Okay, and I'll draw that up here. Okay, so because in my notes I jump right into the inspection method, and I want to do the more basic method first. Okay, so example, and I'll just call it example number 1. Okay, actually this is example 3.1 anyway. The same thing. Solve via nodal analysis. And so what we'll do is we'll lay down the basic steps that we use to do this. Okay, so what does the circuit look like? It looks like this. Okay, so this is called IA, this is called IB, then we have R1, R2, R3. R1, R2, R3. Okay, so first step in doing nodal analysis is gonna be to label everything like usual, but now I'm gonna put a little caveat. I'm gonna say especially the nodes. So actually the way I'm gonna say is I'm gonna say label the nodes and then plus everything else. Because I wanna highlight how important it is that you properly label the nodes. Because if you don't, if you have a screw up in terms of labeling the wrong number of nodes or labeling two nodes that are electrically equivalent as different nodes, then it's going to make the problem very difficult to solve. So how many nodes do we have in this picture? Good guess. Very close. And that's probably the second most common answer is going to be 4. It's 3, actually. Okay. And one easy way to do this is to travel around the circuit. Okay. So what I'm going to do is I'm going to pick a starting point right here. That's going to be 1. And what I'm going to do is go from point to point and just, in my head, ask myself, is this a new node or not? So we go from here to here. Is this a new node from 1? It is, right, because we have a branch in between the two of them, which we expect to have a non-zero voltage across it. So we can set that as number 2, node number 2. We'll go over here. Is this going to be a different branch than a different node than 1 or 2? It's not. Then we go down here. Is this going to be a different node than 1 or 2? Should be, because it's separated via branches from both. So I'm actually going to draw it down here. Okay, because we can pretty easily see we go from here to here to here is all 3. And then I travel to the last point, and that's the same as 1. So we've gone all the way around the circuit. And so we see is we have 3 nodes. Okay? One other thing that you have to do in these circuits is you have to define a reference. Now, a lot of students get confused between a node being grounded and a node being the reference. Normally, if a node is grounded, you'll pick that to be a reference node. You don't have to have a ground in the circuit to have a reference node. It could just be the neutral. Anyway, it's getting into a lot of confusing things. But if you see a ground, like if you look at the picture that's in the book, okay, you see that they have node number 3 grounded, which usually gives you a pretty good hint that that's the reference node that you should pick. You can solve the problem using any of the nodes as the reference. It just changes the equations that you're doing. Okay, so we'll choose 3. Say the 25th, 26th? 26th. All right. Now the other thing is, if you remember up top, we used this variable called n, and I know I didn't do a very good job of describing what n was, but now we're going to talk about it down here. So n is the number of nodes, okay? Yeah, I'm going to use uppercase n. I know I'm switching. So this is n. So our n is 3. And that means, hopefully this is starting to make a little bit more sense. Our matrix, our admittance matrix for this is going to be a 2 by 2. Because we have 3. All right, step 3. Step 3 is going to be to write out KCL for both non-reference So by choosing node number 3 as the reference node, we're going to be referring our voltages to that. Okay? So we're assuming that the voltage at node number 3 is 0. And therefore, whatever we get for V1, that's going to really be V1 minus V3, the difference between them. Okay, so let's write out our KCL. We have 3 branches that are adjacent to node number 1, 3 branches that are adjacent to node number 2, and I didn't really label some things here, so let me take care of that. Okay, I'm going to call this V13. I'm going to call this I1. Actually, I'll call it I13. This right here is going to be I12. The voltage across it is going to be V12. I don't even have to write that. And then this right here, this current will be I23, and we're going to call this V23. So, I mean, really, I didn't have to write these because the good thing is by numbering the nodes, they're self-explanatory. I23 is going to be the current flowing from node 2 to node 3, although that's not really, I guess you do have to define it for this branch because IB also flows between those 2. But V23 is relatively self-explanatory. It's the voltage differential between those 2. Okay, so now we got everything written out. Okay, so let's do KCL for node number 1. So what is that going to look like? We have 3 branches, which mean there'll be 3 currents, right?
IA is equal to I13 plus I12.
Exactly. Bingo. And then node number 2. Anybody else? Where?
I12 plus IB is equal to I23. Or
I just want to make sure we keep our directions right. So IB is, yeah, is heading the other
I did
direction.
error one way. So I12 is equal to IB plus I23.
Great. Okay, so we got that. Now, so we've written out KCL for the non-reference node. Step number 4 is going to be to substitute for unknown currents or non-constant right, so there's 2 currents in here that are known. IA is a source, so it's known. And IB. So maybe this should say, instead of non-constant, non-source. With Ohm's law. Okay, so let's write this out. So number 1, IA equals, and so what is I12? Ohm's law, right, tells us it'll be V1 minus V2 over R2 plus V1 minus V3 over R3. Okay, and then for node number 2, we'll have V1 minus V2 over R2 equals IB, which is known, plus V2 minus V3 over R. I labeled one of the resistors wrong. That one up top should be R1. Because R1, yeah, this is R1. That's 1. Okay. So now, the thing that you have to notice here is that because node number 3 is the reference, we can consider V3 to be equal to 0. So that means this and this, okay, they are references, so they're going to be equal to 0, and they're going to go away. And that's good, because in the end, we want to end up with two variables that we're solving for. We have two equations. Okay, now the next step is going to be to put these equations in a form like below. Okay, so we have two voltages that we're trying to solve for, which are V1 and V2. We have an admittance matrix, which I'm just going to call Y. And then we have I1 and I2. Okay, so this is going to be what size matrix? 2 by 2. And these right here are known, and this is what we solve for. Okay, so to get an equation that looks like this, we need to separate out all the v's and group them and get their coefficients. So that's what the coefficients of the v's are. What are inside of this matrix right here. So let's and we need to pull the known currents over to one side. So let's do that. So the first thing I'm going to do is I'm going to pull. We already have IA on one side of this one. That's good. And then I'm going to do is I'm going to get the coefficients of V1. So V1, you can see, has 1 over R2 plus 1 over R1. Okay? Now, what about the coefficients of V2? There's only one coefficient, which is negative 1 over R2. Okay, now, what about IB? So to do that, I got to pull this over to the other side. So what are the coefficients of V1 going to be? So the coefficient of V1 is going to be 1 over R2. And what are the coefficients of V2 going to be? They're going to be negative 1 over, because this is going to move to the other side, right? So it'll be negative 1 over R3 plus negative 1 over R2. So negative 1 over R2 plus negative 1 over R3. Now, I'm going to do something here which is not going to make sense right now, but it's not prohibited, and it'll make sense later. So I'm going to multiply both sides by a negative 1, okay, which is just going to change the sign of everything. You will see in a second why that's really just to fit the form they have in the book. So that didn't change our equation, it just flipped all the signs. Okay, and then the last thing we got to do is put this in a matrix form, a lot like what's shown up here. So we know, and this time I'll use V equals IZ. Okay, so we know that IA minus IB equals some matrix, which we'll fill in a second, times V1 over V2. Or sorry, V1 and V2. It's an array. So, now, what are these elements? What is the top left element? So if you remember the way that matrix math works, right, you take these two, you multiply it by the top row, and that's what gives you that. If any of you are, don't have a good memory of matrix multiplication, that type of stuff, that's another thing that you should probably do a quick refresher on it. Again, it's not, and I'll write it up here real quick, it's not super crazy, right? If we have A, B, C, D times E, F, right? I'm just doing this symbolically so you see the answer, right? So then what is going to be, first off, this is a 2 by 2 times a 2 by 1, which means the answer will be a 2 by 1, okay? So you have a 2 by 1, and I'm just drawing it wide because we're going to need some room. So what is the top element going to be? It's going to be this times that. So it'll be A, E, plus B, F. The bottom row will be C, E, plus D, F. Yes?
And you can only move them together because this move, I don't remember what he was saying, like you give a 2 by 2 times a 2 by 1, right? It's like a 2 by 2 by a 3 by 1.
Well, that's not allowed.
Right.
The rule is, right, that these two numbers must match.
Right.
Yeah. So you can multiply a 3 by 4 with a 4 by 6, and you end up with a 3 by 6. But those two have got to match. Unfortunately, this isn't a linear algebra course, so I can't spend a huge amount of time on it. You guys should have seen this before, and it's really, I mean, once you do it once or twice, it's not super difficult. Okay, and the good news is we're not going to do really too many other linear algebra things. We're not going to be doing inversions by hand. I'll talk about it a little bit, but there's some like diagonalization and all that type of stuff that you do in linear algebra, and matrix multiplication is going to be pretty much where we stop. Okay. I see some faces that are not looking too happy with it. It's not that bad. Okay, so if you take this right here and you apply it, you take this rule and you apply it to what's right here, then we can pick apart the pieces that we need. Okay, so this is this. Bingo. These are the two variables. So now we just have to figure out what are the coefficients. First thing is that the top equation corresponds to the top row. Bottom equation corresponds to the bottom row. So what times V1 gives you IA? Yeah, this element right here, right? What times V2 gives you IA? This. So this is going to go right here. This is going to go right here. And then on the bottom, what times V1 gives you IB? You put that piece down there, and then, okay, hopefully that makes sense. Okay, so we have down here 1 over R1 plus 1 over R2. Then we have negative 1 over R2. This is also negative 1 over R2, and this is 1 over R2 plus 1 over R3. So that's the final form of, well, not the final, that's the equation, the form of the equation that we want to get into. And then, what we can do
Can you go back to the equation?
Sure. I'll leave that up there for a second. That's a good thing. Copy stuff down. All right. So, now the rest of it you can pretty much do in your calculator. So let's assume that we had values for R1, R2, and R3. Then what we would do is step 7, which would be to invert the matrix, multiply, and solve. And again, this would all be in your calculator. Because we take this form of the equation right here. This is your, I'm just going to refer to this as Y matrix. And then so to get the answer, all I got to do is say that V1 time, or V1 and V2, that array is equal to the inverse of that times IA negative IB. And all this stuff is known. And so you can just go ahead and solve in the calculator. So if we do a numerical example, which I can do pretty quickly on the computer, hopefully. I don't think they have MATLAB on this, right? I'm not using MATLAB because I'm trying to be fancy. I'm just, I don't have a calculator I can put on the screen. So, don't worry, I'm not going to be doing anything crazy with this. So all I'm going to be trying to do is put our matrix into MATLAB and then just invert it and solve, which you'll be doing in your calculator. So the R1 value is 12,000. The R2 value is 6,000. And the R3 value is also 6,000. IA is 1 milliamp. And IB is 4 million. Okay, so now what I got to do is I got to build this matrix down here. So, and again, you'll be doing this on your calculator. So the Y matrix will be equal to, okay, we're going to have 1 over R1 plus 1 over R2. That's the first. Then we're going to have negative 1 over R2. That's the 1, 2 element. Then we're going to have that. And then we're going to have 1 over R2 plus 1 over R3. Okay. And so those are the values of the matrix. The currents are simply IA and then negative IB. Don't get too caught up in the syntax and stuff like that. Again, you're not going to be doing it in MATLAB when it comes to quizzes and stuff like that. And then now we got everything we need. All we have to do is say V equals the inverse of Y times I. And that's our answer, hopefully. what do they get? They get the same thing. Okay, negative 6 volts and negative 15 volts. Actually, if you look in the book in example 3.1, they have some MATLAB code in here that you can, but again, you're going to be doing on the calculator, so try to do that on your TI, whatever. So, what are the pros and cons of this method? The con is, right, it's a very formal method. You have to set up matrix systems of equations and all that stuff. The pro is that once you get it set up, boom, the answer comes like that. There's no simplification, expanding it back out. And this may be harder when you're talking about a matrix with 3 nodes, but when you're talking about a matrix with 7 nodes, then all the overhead that's associated with this pays off. Because trying to do really large circuits the other way, okay, the way that we did in chapter 2, ends up turning into a disaster pretty quickly. Okay, so if you solve in MATLAB, so if we were to solve in MATLAB, we get negative 6 volts equals V1 and negative 15 volts equals V2. Alright, so that's nodal analysis, the most basic implementation, which is determine the number of nodes that you have, make sure to label everything properly, set up the KCL expressions, in case you have the same number as the number of nodes minus 1. Put the KCL expressions into the right form, which essentially moves all the known currents to one side, and then you isolate the coefficients of the V's. You put that into a matrix, and then you can just plug in numbers and you can solve. Any questions on that? So now, the next thing is, how can we make this easier? So what I'm going to show, I want to put up here, is I want to put up the circuit, and I want to, if I can get it all up here, and I want to put up the equation. When there's only independent sources like what we have it set up right now, there's a shortcut to doing this. So the first thing, well, can anybody tell me anything they noticed about that matrix at the bottom? It may not be that evident because it's only a 2 by 2, or maybe because it's 3 by 3, it'd be a little bit more evident. But the off-diagonal elements are equal to each other. Okay, element 1, 2 is the same as element 2, 1. So let's write some things down that we notice. The first thing we notice is that the off-diagonal elements are equal. Another thing, if we look at this back here, is you'll notice that a resistance only shows up in a value in a KCL for an equation if it's adjacent to that node, right? You see, like if you look at element 1, 1, it includes R1 and R2 because those are the two that touch it. R3 doesn't touch it. So you don't see R3 anywhere in the first row, you don't see R1 anywhere in the second row. Okay? So only adjacent branches show up in what we'll call coefficients for the node. KCL. Okay, and again, what I'm trying to say is that we don't see any R3s up here, we don't see any R1s down here. Another thing we can notice is that the diagonal elements are positive and the off-diagonal elements are negative. Okay, that's a rule that's gonna stick. Diagonal elements are positive. Off-diagonal are negative. Okay. Now, what about the elements themselves? Right, you see that the off-diagonal elements only include the admittance or the resistance that's in between them. Right, you see element 1, 2 includes the resistance that's between 1 and 2. Obviously, there's going to be no resistance between a node and itself, right? Doesn't make any sense. So the diagonal elements, they include everything that's adjacent. Okay? That's another thing. So diagonal elements include all adjacent branches. Off diagonal include only one. The one that's in between them. So anyway, and then the last thing we can pick out is that the left-hand side of the equation, why do you think IA is positive? Try to move everything more this way. Why do you think IA is positive and IB is negative? I'm trying to get this in the right window. Here we go. Okay. What's the difference between IA and IB in the picture? IA's, say what? Yeah, so IA is going into the node, IB is coming out of the node. So the currents are positive if going into the node, negative if exited.
Are you talking about a particular node?
Exactly, because remember this equation right here corresponds to node number 1. So for that one, we're talking about node number 1. IA is entering node number 1. For this one down here, the second, the bottom half corresponds to node number 2, and IB is exiting node number 2. You can't get mixed up because, right, a current is always going to be entering some node at a certain point, but we're talking about the node that's specific to that equation that we are. Okay, so if we take a look at all those different things that we wrote down, you can see that we could probably put these rules together into what we're going to call an inspection method to generate the matrix. And the reason why that's good is because it eliminates a lot of writing out equations, and if you can skip straight to the end, why not skip straight to the end? Okay, so let's all right, so how do we define a matrix equation by inspection? So So I'm going to draw a big version of this, and we'll try to insert everything. So over here, we're going to have our currents, okay? And so what we're going to have is, I'm going to call this node number 1, and then we'll have other nodes below. So current, source, entering, node number 1, right? Then we would have current, source, entering, node number 2. Okay, and then, right, this, obviously this matrix could be really big, so I'm not going to keep writing. Okay, so that's our I. So this is the I array. That's going to be equal to, and now we got to define the Y matrix. And so this is the big one. Okay, the first element that we have to define is going to be the top left diagonal right. And I'm going to, so this is going to be element 1, 1. Okay, and so this is going to be the sum from k equals 1 to n. We're going to explain what this means. Of 1 over R1k. For all adjacent branches. So how does that correspond to what we have over here? If you think about it, we have two adjacent branches. There are R1 and R2. So that corresponds really nicely to this. Because really, and this is a little bit of a naming thing, R1, a better way of referring to that is that's R12, right? And this one's R13. So this is the sum of all the resistances, R12, R13. Now the next one. The off diagonal is going to be the sum, and this is element 1, 2, is going to be the sum of -1 over R1, 2. And the only reason why I put sum is because there could potentially be more than one resistance going between those two branches, right? You could have two parallel paths. So I'll say for all parallel paths between 1 and 2. Okay, and then this is going to be the same as 1, 2. Okay, that's going to be the same as that. And this is going to be the same as 1, 1, but for node number 2. Anyway, so hopefully you're getting the idea of what it is that we're trying to. And then lastly, you're going to have your V1, your V2, etc. I can't erase the other rest of the Anyway, so writing it out formally takes up a lot more time than actually doing it. Because hopefully now, if you were to take a look at a picture like this, you should be able to rattle off the admittance matrix to me relatively easily. What's going to be element V? What's going to be element 1, 1? It's going to be 1 over R plus 1 over 2. What's going to be element 1, 2? Negative 1 over R2. What's going to be the other off diagonal? Same thing. And what's going to be element 2, 2? It's going to be 1 over R2 plus 1 over R2. It's a lot easier to do in practice than it is to try to write out. And then what you end up with is the same equation that you did down here. So to do this problem, you essentially skip the whole everything that we wrote on this paper. Now, I want to caution you, the inspection method, at least the way that we've defined it, only works if, first off, we don't have any dependent current sources or dependent voltage sources. And actually, the way this is set up, it doesn't take into account for voltage sources, right? Because we don't have any way to include voltage sources in there. We will in a little bit, but for right now, we don't. Okay, so, I mean, that was a lot of information. That's essentially nodal analysis. That's the basics of it. What we're going to do from this point forward is make adjustments to it to account for different cases, where we have dependent sources, where we have voltage sources, et cetera, going on. Okay? This is probably the easiest case. The easiest case of nodal is going to be current sources only, or current sources, independent current sources and resistances only. For quizzes and stuff like that, if I don't say that you have to write out the equations, you can feel free to do inspection. I'll tell you though, when you're doing homework problems, don't skip to inspection too quick, because you do want to get familiar with writing the equations. The harder problems, those are the ones where you're going to have to definitely write the equations. So you don't want to become so reliant on the inspection method that when the time comes, you are not familiar with that. All right. So, in the board notes, I have an example, or part of the example. I talk about how to do the example, how to do this problem using the reference node as node number 2, which I'm not going to go over because we spent a lot of time on this stuff anyway. But you'll see that you can do it using node number 2 as the reference, and it switches up the equations, but you end up with the same answer. Okay, so now let's talk about the next case. So the next case is going to be circuits with dependent current sources. And so, so when you have circuits with current sources, the big picture is that you're just going to have to write out the equations and do it the good old-fashioned way. The inspection method, I mean, there's some pseudo-inspection methods that you can use for dependent current sources. Really, at this point, I don't think that they're going to be worth your time to learn or memorize. So when you see problems like this, you're going to have to just write out everything. So let's take a look at something that looks like this. So this is almost exactly what we had last time, except we replaced one of the independent current sources with a dependent. Okay, so this is called beta I23. So it's a current controlled current source. This is going to be, and I'm going to go ahead and just label the nodes for you guys. So this is for you guys. So this is node number 1, this is node number 2, this is node number 3. 1, 2, 3. This will be called R13, R12, R23. And this is IA. Okay. So could we try to do this by inspection? Yes. But then what you would have on the left-hand side is beta I23 instead of a constant, which is going to totally screw up, right? This form right here, it only works because we assume that we can invert this matrix and multiply by that, and that means that this has to be a number. So if we have variables over there, it's not going to. So for this, we're going to have to go ahead and just write all the equations. So step number 1, and I'm going to say label what you need from now on. We don't necessarily need to label everything anymore. Step number 2. Okay, one thing that is really important is going to be making sure that we know how many nodes we have, what the size of the immense matrix is, and all that type of stuff. So since I already gave you the nodes, you should know that n is equal to 3, and so our Y matrix will be a 2 by 2. Okay? So let's write out KCL for node number 1. So what's KCL for node number 1 going to look like? And we can just refer to things like this. Like this is I13, this is I12, and we'll call this right here I23. So what's KCL for node number 1 look like? We all failed this class. No one's answering this? Come on. Believe it or not, I do know the answer. I've tried a couple of times. So. Yes?
For node 1, right?
Yep. Yeah, the beta I2, whatever, I got you. So beta times I23. All right?
And then is equal to I13 plus I12.
So what'd you say in the middle there?
It's equal to I13.
So here's where you got to be careful.
Oh, wait, it's going to go over.
Yeah, so I always recommend that for KCL, people just use the form of things sum to 0. Because when you do the entering equals leaving, then, in my opinion, it lends itself to making a lot more mistakes. Because if you take a look at it this way, you can just say all the currents entering the node equals 0. So what is this current entering the node? It's negative beta minus I13 minus I12 equals 0. I don't know if it's easy or not, but for me it seems a little bit easier keeping the side straight. Okay, now for node number 2, what about that? Just summing together all the currents that are entering the node. Yes?
I12 plus IA minus I23 equals
Sure,
0.
yeah. Right, so we have I12 plus IA minus I23 equals 0. Good. And then the rest of these steps are a little bit mundane. So step number 3, substitute. And now the main difference is instead of just using Ohm's law, we're also going to include the expression for the current controlled current source. So, let's do this. So 1, what is I23? It's V2 minus V3 over R23. What's I13? It's going to be V1 minus V3 over R13. And then here we have V1 minus V2 over R23 equals 0. And these are all negative, so I can just go ahead and make them all positive. V3s are all going to go away because they are assumed to be 0. Down here, I'm going to have V1 minus V2 over R12 plus this known IA minus V2 minus V3 over R23 equals 0. And that goes away. And then so now, hopefully we can skip a step. And sort of imagine what this is going to look like in matrix form. Okay. So for up here, we're going to start out by doing the current array. So for this up here, is there any constant that's going to go on the left-hand side of the equation? There's not, right? There's no, everything here is a coefficient of either V1 or V2. So that means we'll have a 0 on top. Down here, are we going to have anything on the left-hand side? We do. We have this IA. So we'll go right here. Okay, so that's that. Next, the matrix. So what are the coefficients of V1 on this top equation? We're going to have 1 over R13 and 1 over R23. Okay. What is going to be the coefficient of V2? It's going to be 2 pieces, right? We're going to have negative 1 over R23, but we also got to take into account this. So we'll have negative 1 over R23 plus beta over R23. Okay, now down here. Yes?
Why isn't that 1 resistance the last term in the first equation? Why isn't that R12?
Yeah, I think I made a mistake. Yeah, that should be R12. You're right. So that means that this right here would become R12, and this would also become R12. It's a little bit hard to read, but we'll clear it up in the next equation. Okay. Now, down here. So the tricky thing about this one is you have to imagine putting everything on the other side, because if we consider IA to be positive, another way we could do this is we could just shift IA to the other side. So we'll make IA negative, and now we have both these with the same sign that they have right now. So what's the coefficient of V1? It's going to simply be negative 1 over R12. And what's going to be the coefficient of V2? It's going to be, sorry, this is a positive, right? Positive 1 over R12. What are the coefficients of V2? It's going to be negative 1 over R12. Minus 1 over R23. And so we multiply that by V1 and V2. So I'll rewrite that. But this is the equation now we end up with, taking it from above. Now, if you wanted to make this a little bit easier to understand, and I tried to do this a little bit more quickly, is rewriting that equation. Because if you rewrite this equation in a more nice form, like the way we did for this one, right, you'll see that it becomes a little bit easier to pick the matrix coefficients out. So that's up to you, how you want to do it. In the beginning, you might want to stick an extra step in there where you separate out the IAs and group everything by the coefficients, but it's not super hard to do it in your head. All right, so let me just rewrite that because it's really messing with it. Okay, so anyway, that's the nicer way of writing it out. Hold on, I'm trying to figure it out. I'm just checking with the answer that I got from make sure everything's the same in the answers, right? Okay, so that's right. And then the rest of it, I don't think I need to go through, right? The rest of it, that's something that you're going to have to become familiar with when you're putting it in the calculator form. Once you do it a couple of times, it's really not that hard. Okay, so the next version that we're going to talk about. So what about the case where we have independent voltage sources? So let's imagine for a second that I replace this right here with a 5-volt source. Okay. How would that change the way we solve this? So this takes a little bit of higher level thinking, at least for a second. Let's go to the end. The end game, what are we trying to solve for? We're trying to solve for V1, and we're trying to solve for V2, right? That's what we're trying to get at the end. So if I give you that there's a 5-volt source right here, I get just one of the answers. Okay? So independent voltage sources actually are very nice because they take away things that you got to solve, assuming that they're in between a node and the reference node. Okay? If you have a voltage source in between a node and a reference node, all of a sudden that one goes away. So now, when you have this problem, you only have to solve for one of the node voltages. So you only need one KCL equation. So you can eliminate the KCL equation that's associated with this node number 1. So that's essentially how we treat it. Now, what happens when we have a voltage in between two nodes? Okay, let's say that I have a 5-volt source right here. And what I'm doing is, since we're getting close to the end of class, I'm going to kind of just do a preview of what we're going to do next time as opposed to jumping into another example. So, how do we treat that? Let's say we had a 5-volt source in between these two nodes. If you remember, we said that KCL didn't just apply to a node, it applied to entire sections of the circuit. So we could actually apply KCL to this entire chunk, which would say that beta I23 would be equal, anyway, I'm not going to go through all the signs, but you could sum all the currents entering and exiting this whole chunk to 0. So what we can do is if we have a voltage source in between these two nodes, we can consider this to be a single node. Okay, and the term we're going to use for that is we're going to call it a supernode. And the reason why that helps us is because if we know there's a 5-volt differential between these, we only have to solve for one of the voltages and we automatically have the other. Okay, so what happens is you have one KCL equation which considers these two pieces to be a single chunk, and then at the end you can use the 5-volt difference to calculate one from the other or vice versa. And then the last case, which we haven't considered, because we did independent current sources only, we did dependent current sources. That would, what we just discussed, would address independent voltage sources. And then lastly would be dependent voltage sources. And dependent voltage sources, you treat them a lot like you treat dependent current sources. Meaning that you have to just write all the equations, and you have to massage the numbers and put them in the right form. So, I don't want to get started on another example today because I think we've gone through a lot of them. So I'll stop there. I encourage you guys, since this is fresh in your mind, and this is really one of the more fundamental things that we discuss in this class. What I mean by that is you've got to understand this. Okay? If you don't, it really takes a toll on how you do the rest of the course. So I really encourage you to do at least one nodal analysis example today, even if you don't have a chance to do a lot of work on the homework or whatever. And that way you can come next time with any questions if there's something that really cares. So keep chugging away on the homeworks and come to me with any questions in class or outside of class. And I guess that's pretty much it then. Have a good week.
How was it overnight? Seems interesting. You know anything about it?
Is Jamie here? Darren? Jamie? There we go. I keep just holding on to paper. No worries. I'm just joking. Sure, go for it.